Instead of some crazy project like usual, this video is going to be nice and simple. I'm going to show you how you can make your own custom rubber tires and see how well they compare to other common methods. There are 4 types I want to test: regular PLA and TPU, which can be printed directly, then printed ABS with a spray-on rubber coating, and finally actual solid rubber tires made with liquid resin. First up is making the rim and the mold for the cast resin tires. The rim is the part that I will be casting the rubber onto and is what will then be attached to whatever motor I plan on using. In this case, I'm just copying the design of these RC car tires so I can test these out on it once they're done. It's important to make a step that properly aligns the rim and the mold so it stays centered and doesn't end up making a wobbly tire. There should also be a good bit of contact between the face of the rim and the mold, so when the rubber is poured in, it can't easily seep past and into the inside of the rim. The rim also needs some way for the rubber to lock into it. Otherwise the rubber will slip off after some use since it doesn't adhere very well to printed plastics. I cut slots through the inside of the rim with several holes reaching the outer surface. That way the rubber can flow in and wrap around the plastic so it doesn't slide off. After making a few of these, I also found it very useful to add a funnel edge to the outer part of the mold and also make a separate part that sits on top of the rim to act as another funnel to help keep the rubber where it's supposed to be. Up until this point, I've only ever made smooth tires with no tread. But to more closely match the tire I'm copying, I added treads to this one as well. When making molds like this, it's super useful to use Boolean operations in CAD software. That way, I can use the outer mold and the rim to make the tire without needing to model it separately. Even though I'm not actually printing the tire portion, it's still useful to model since it'll let me make sure the final tire looks the way I want. But more importantly, I can use it to find exactly how much resin I will need to mix up so I won't need to guess. The outer mold needs to be printed in sections so I can actually get it apart once the resin cures. For smooth tires with no tread, I usually only do a 2-part mold, but I'm going to split it into 5 sections this time to make sure it'll still come off without the tread getting caught. I also made a simple clamp to hold everything tightly together so it doesn't move or leak when I'm pouring in the resin. With the modeling out of the way, I printed a bunch out on my new printer from Bambu Lab. Out of all the different printers I've worked with, the X1C is by far my favorite. Everything from the software, to the AMS for printing with multiple materials, to the printer itself is heavily based around making it as easy as possible to use. The best way I can put it is that I want to print stuff for my hobby, not have printing stuff be my hobby. And this setup has needed basically zero manual adjustment or fiddling with like a lot of other printers do. The printer itself has automatic bed leveling that uses both force sensors and the LiDAR sensor on the print head to cross-check the results. The LiDAR also lets it scan the entire first layer to ensure it printed properly, and will automatically stop the printer if it didn't. It has a built-in camera that you can use to monitor prints through the app, and it even uses that camera to automatically detect failed prints. I can say that the print fail detection does indeed work, but chances are you won't even end up needing it that much. Since I've had this printer, I've already run about 7 spools through it, and I've only ever had 1 failure. Changing materials is also super easy with the AMS. Filament from Bambu Lab comes with these RFID tags that allow the printer to automatically detect the type and color of the filament. Originally I was kind of skeptical that this was some way to lock you into buying only their filament, but you can manually set it if it's another brand super easily. It then syncs all that with the slicer software to automatically use the correct settings. Use the link in the description to check out this printer and other products from Bambu Lab. I printed all of the parts out with PLA except for the rim, which is ABS. I'll go into why a bit later. When casting anything, it's important to use mold release on all surfaces you don't want permanently attached to the resin. Even though the resin itself doesn't really bond to PLA, I find spraying everything with it anyway makes it much easier to get apart once it cures. I also usually put a small amount of Vaseline around all the faces of the mold sections that are supposed to seal. Even though the mixed resin is quite thick and doesn't typically leak through much, adding this helps make sure it doesn't. I also add a bit to the bottom face of the rim to keep the resin from leaking to the inside. After that, I clamp the mold together and let the mold release dry for another 20 minutes. The rubber I'm using is a urethane resin from Smooth-On. They have a bunch of different hardnesses, and for this video I'm going to be testing the 30A version, which is pretty soft. The volume of the urethane section can be found in CAD, and the density of the urethane can be found on the product page. Using these, I can calculate that I need about 120 grams of urethane, but I'm going to mix up 140 just to have a bit extra. The resin needs to be measured out 50-50 by weight, which comes to 70 grams for each part. Smooth-On also sells dyes to color the urethane, which should be added and mixed into part B before part A is added. After thorough mixing and scraping the sides of the container a few times, it gets poured into the mold. Unlike most resins, Smooth-On says this stuff doesn't require vacuum degassing, but if you have a vacuum chamber, it doesn't hurt to do it anyway. When casting these tires, I typically pour in most of the rubber, then vacuum it a bit to make sure the rubber thoroughly reaches all of the little pockets inside of the rim, and in this case the tread too. Using larger slots in the rim or different tread types would probably let you get away with no vacuum chamber at all, as long as you take care to slowly fill the mold and not trap big air bubbles. After the vacuum removes most of the air, I pour in a bit more rubber, ensuring that there is some extra above where the top of the tire is supposed to be. That way, if any resin leaks through the seams in the mold, it won't immediately make the tire too short. The resin should be left to cure somewhere at least 65 degrees for about 24 hours. After that, the mold can be carefully pulled off and usually reused. The extra rubber on top is cut off and the tire is finished. Optionally, the resin can further be cured by heating it to 150 degrees for 8 hours to get some extra toughness out of it. This is why I printed the rims out of ABS instead of PLA. I previously tried this with PLA rims and they ended up shrinking enough that they wouldn't slip over the motors like they were supposed to. So if you plan on doing the extra heat curing, be sure to either use a higher temp plastic, don't make the rim have any precise fits, or do what I did and just put the rim on the motor it's supposed to fit over before putting it in the oven so when it's done it'll still fit. Next up are the solid PLA tires. They don't need anything special done, so they're good to go right off the printer. The ABS ones, however, are going to be coated in some Flex Seal spray on rubber. The reason I went with ABS instead of just printing out another set of PLA is because ABS tends to be more easily dissolved by solvents than PLA is. Similar to how you can easily vapor smooth ABS prints, but it's a bit more challenging with PLA. My hope is that the solvents in the Flex Seal will dissolve the ABS somewhat and allow it to bond better so it doesn't easily peel off. They all got a few heavy coats and were left to dry for a few days before testing. For the final TPU tires, I designed them in sections so I could print the materials separately. The AMS lets the printer switch between materials while printing for stuff like multicolor parts, or what I find the most useful, supports that don't bond to the base material as well so they can be removed much more easily. However, since TPU is so flexible and prone to jamming, it's recommended to print it directly without the AMS. This being the reason why I printed the outer tread portion out of TPU separate from the PLA rim that it locks onto. While printing out the TPU sections was the first time I had a print fail on this printer. Luckily, the camera detected it pretty quick and automatically stopped before much of anything happened. After that, the rest of the TPU parts and PLA rims printed just fine. Now with all the tires made, I can move on to the testing. I tested each tire against a concrete block with a constant force. The first test is for static friction. The motor slowly ramps up the torque until the tire slips. PLA slipped first at 0.66 Newton meters, TPU at 0.85, urethane at 1.23, and finally Flex Seal at 2.57. Surprisingly, the Flex Seal came out on top even though it doesn't feel nearly as grippy as the urethane. The next test is for kinetic friction. This time the motor spins at a set speed and measures how much torque is required. This is to see if any materials significantly lose grip once they've already begun sliding. I would like to point out that a lot of the torque ripple is simply caused by the motor controller not being able to control the speed very accurately, as evident by the bumpy speed graphs that should be a straight line. This test is mostly up to your own interpretation, so I'm just going to run through the tests and put the data up on the screen. This final test is a bit more destructive. It sets the tires to run at a set speed to see how well they hold up against long-term wear. Now for this test, rather than doing a constant force for all the tires, I'm going to adjust the force at the beginning of each test so each tire requires about 1 Newton meter to turn. That way, the amount of work going into turning each tire is about the same. It's no surprise that the harder materials lasted longer. The soft urethane was gone almost instantly, along with the thin layer of Flex Seal, so it quickly turned into only the ABS hitting the concrete. TPU actually seemed to do quite well and continued to still have pretty good grip even after the tread was completely worn away. With the formal testing out of the way, now I want to see how well they perform on an actual vehicle. We've made this little track to drive through to see which tires give the best performance, passing over grass, asphalt, and gravel. The goal is to complete the track the fastest. I'll run each set of tires several times so I can get used to them and help keep the results mostly dependent on the tire type. I recorded all the runs with a GoPro on the car so I can go back through the video and time the laps afterward. However, I underestimated how long this was going to take, so I threw together a Python program that plays the video and lets me hit keys when the car passes through the cones to save the times. I then had another program search through all of that data and calculate both the times for each section of track and the total lap time. If I average the best 5 laps of each, the original tires came out in first place at 10.88 seconds, the urethane tires second at 11.53, TPU at 12.34, PLA at 14.55, and in last place is Flex Seal at 15.15. So why did Flex Seal do so bad when it had the best grip in the formal tests? Well, honestly, I'm not exactly sure, but I think it has something to do with how much load the tires were under during the tests. The formal test had about 4 pounds on each tire, which is quite high compared to the car test, which only had about 0.75 pounds. While driving, the Flex Seal didn't seem to have good traction at all, and also wore away quite fast. If I had more time, I'd cast the tire with harder urethane to test again on the bench, and see if it performs more like the Flex Seal did. All of the tires showed signs of wear, with the Flex Seal being the worst, having most of it completely worn off the outer surface of the tires. The urethane has some wear on the inside edges of all the tires, but the majority of all the tread is still there. At first glance, the PLA and TPU didn't seem to change much, other than a couple nicks where I think they hit stones while driving on the asphalt. For a more formal wear estimate, I weighed all the tires before and after driving. To my surprise, urethane did the best this time, with Flex Seal being a close second. Then PLA and TPU both had significantly more wear than the softer materials, exactly the opposite of the previous testing. I can only speculate that this is because the harder materials spent more time slipping and hence more time wearing. They are also likely more prone to getting chunks of material broken off by impacts than the soft rubbery materials. So by these tests on an actual vehicle, it appears the urethane is the clear winner in terms of both wear resistance and grip. So making your own tires out of urethane resin seems to be quite viable and should get you close to the performance of the off-the-shelf tires. Possibly even better if some more effort went into choosing the best hardness and tire design. Something else I'd like to point out is that the urethane casting method isn't limited to only tires. It's easy to print other molds and cast different parts such as bumpers, gaskets, and grippers, where you might need a very flexible or grippy material.